Yeah, the first part investigate.
Yeah, it's probably, they're all different, they're all one way.
Oh boy.
Yeah.
And then it goes hard. And then it goes hard work for all hands, I guess. Yeah.
Yeah, what did you think?
It was fun. It was talked up like it was gonna be like really complicated. And I'm sure it is if you actually have to do it right.
Yeah.
But it wasn't like I understood everything.
I think, well, it's also a third one, so.
Yeah, that's
Yeah,
Yeah, but I didn't. I don't have to do
Yeah, wait, how?
Let's no, you were very nice. I asked a question, you were very nice. Come on.
Was anything like that there?
No, he like looked at me for like a couple of seconds. And then he just kept going.
Like 15, probably like, I don't know what.
Okay, but you had me for 14 seconds.
Yeah, but he.
Oh, and I sat like under his ass. Like,
Well, it's just that now, everyone knows.
this is where
All right, let's start. Okay, so we finished off last lecture with this thing, right? This 2D kernel with the blur. Okay. When's your assignment due? Saturday. Who started it? Come on. Start these things a little earlier. It's not that bad, I think, but please start it. Questions on Piazza if you're confused. Do the quizzes online as well. I might make all the quizzes 2 attempts each to make them a little bit less harsh. Sometimes you just have one small misunderstanding and then you get all 17 questions wrong because you flipped something or just didn't understand one thing. So I might modify it to allow you to do it more than once. The point of the quizzes isn't to make them super hard. It's mostly just to make you sit down and think about it and actually answer some questions. Okay, like a homework kind of thing. Okay. So we finished off here talking about the fact that, we sort of built our first 2-dimensional kernel, right? Where now we showed you that you can actually put loops inside of these things. So the original program here was probably like a quadruply nested loop if you did it on a CPU, because you had to go through every pixel, and then for every pixel you had to go around the radius of each pixel to figure out what its colors were and actually compute the blur. Okay. Again, and this is an embarrassingly parallel problem. There's no real sharing here happening between threads, so it maps itself very nicely to a super parallel machine like the GPU. We mentioned a little bit about sharing. So there is sharing. There's read shares here, where you're all reading the in. All the threads end up reading from the in matrix, and some of the threads are reading, the same values from the in matrix because they're nearby each other. Some of this sharing will get exploited across warps, some won't. Doing redundant accesses to memory. When we start looking at blocking these algorithms, we'll see how you could take advantage of that explicitly with a scratchpad. There is caching on typical GPUs, so you'll get some of this locality, maybe, if they happen to be kind of scheduled around the same time, but you have no control over when the threads are scheduled if you're not sort of doing them inside this, capturing locality inside this scratchpad memory. So it's sort of like it's very difficult to reason about cache tiling in a GPU because there's so much interference from other threads. You could do it in a CPU pretty reasonably, you know, your cache size. I mean, I think you guys even went over optimizations in 565, right? Trying to get around associativity, right? Trying to make sure that you don't end up with, you know, conflict misses by changing your code to that way, because it's so, you know, that there's only one thread competing for the cache. If there's another thread, it's like there's like 100 or 1,000 of them competing for that same cache. You don't know how much cache you're actually going to get, right? Because they'll be interfering with each other and kicking stuff out. Questions on this? All right. So we talked a little bit about Ocean. There's a bug in this code. Somebody pointed out in Piazza very rightly that there's, you know, you're basically walking off the end because there's no guards in here. If, you know, if I is 0 here, then you're going to index in at -1, which is obviously not going to give you what you want. And it'll either seg fault, or if you've allocated the memory, it'll just read some garbage. So yeah, this, you know, I think in the quiz, we asked you to translate this into a like a CPU or a GPU program. The quiz is structured such that you didn't notice this bug and you just sort of blindly did it. Even if you notice the bug, I don't think it really has material effect on any of the answers. But, you know, to fix this, you could either pad it out so that, you know, you had one extra row on the input matrix, or you could one extra row and column, or you could basically just add the if condition in here to correctly go around instead of you know, indexing these zeros. Yes.
If you choose between them, that changes the answer to the last problem.
Why?
Padded, then there's no loop in the kernel. But if you have an if condition, there might be. Like
Why do you need a loop? Because you could do it to test to see if each -1 was, yeah. Or you could do it without a loop too. You could just test to see if either one is over, but yeah. So maybe there's some ambiguity. Answer the quiz as though you didn't notice that there was walking off of either edge. Okay. And we'll sort of fix this code for next year. You know, I can post what you would do without the loop, right? You just test, you put ifs in there to make sure you don't walk off the end, essentially. Okay. So there's some quizzes online that sort of test your knowledge on this. Pay attention to the setup of the quizzes because, you know, what is X and what is Y is important. And if you invert them, you might end up just getting everything wrong. So pay attention to the instructions in the quiz. All right, let's talk a little bit more about the programmer visible hierarchy. Eventually in this class, we're going to start talking about architecture and microarchitecture. But right now we're talking about what CUDA programs see, what the user sees. So we talked about registers. Every thread has its own private register space. So when I load into a local variable, only that particular thread has access to that local. There's global memory, which is sort of where all the mem copies go. This is the HBM, if you're thinking about the sort of device memory on a typical PCIe card. And then there's these other structures we've added here, one called constant memory, and then one called shared memory, okay? So let's start with constant memory. It's sort of the easiest. If you've got constants in your program, they go into constant memory. When you call something const, it goes into this constant memory space and it's cached. There's like a sort of an efficient constant cache that exists inside the machines. There will be values that every thread wants to read that are never modified. Those go in the constant cache. There are limits on how big you can make the constant memory, so you can't put everything in const. But for the stuff that's shared amongst all threads, it makes sense to sort of put it in this constant read-only memory. And this stems from graphics. There's lots of stuff in graphics that is constant across all of the pixels. So you put these constants in that memory, and then CUDA allows you to access it. Okay, so you'll see these things called constant loads if you look at the assembly ISA, which are loading from this memory space. Nominally, it's all backed up by the HBM, right? There's a specific cache that's caching the constants. It's some range of the address space is devoted to the constant memory, and it basically you have a few pages in the main memory system that are devoted to your constant memory. Okay, and then there's this thing called shared memory, which is a really weird name because when you think shared memory, you think like 666, right? Like a shared memory multiprocessor, right? The reason you do all this coherence and consistency stuff is because the processors share memory, right? All of the processors in the system are sharing memory system and then they're caching it. The shared memory in CUDA is a scratch pad. Okay, it's not shared among all threads. It's only shared among the threads in a block. So when we're talking about blocking algorithms and these things called thread blocks, you basically every thread block gets its own chunk of something called the shared memory. And how much it uses is up to the programmer. It's dependent on how many threads the programmer wants. How much they can basically specify, I want this shared memory to be 1 megabyte or whatever, right? You basically specify these constants when you spawn the kernel. And then when each of the blocks are scheduled to each of the cores, there's more shared memory on each core than maybe one block will need. So then there's an allocation policy that cuts it up among the concurrent blocks that are on the core. So if you look at this diagram, it's basically got the yellow is the thread blocks, okay? And so it's showing you, and the green is the threads. So each individual thread has access to some private registers, and then threads within a block have access logically to the same shared memory. So if one thread 0 in a thread block, writes to an address in the shared memory space, and then another thread in that same block, not necessarily the same warp, reads from that value, it will be coherent, okay? You will see that update. Now, you're going to have to manage the scheduling because the timing of the writes and reads is not necessarily guaranteed. And so what they do is they provide a fast barrier mechanism so that I can guarantee that all of the threads within a block have made it to a particular line of code, so that if I'm doing a bunch of writes to shared memory, I know that all of the other threads are done with their writing before I go read something that somebody else wrote. It's like a very coarse-grained way to keep the threads within the block synchronized. There's also fast atomics on the shared memory. So if you wanted to create your own mutexes, et cetera, you can do that and it won't be a performance hog because the shared memory is on chip. Okay, it's very close to it's the SRAM that's inside each of the SMs, and you can do fast atomics in that space. The slide here also gives you a sense of how long each of these things take from the processor's perspective. So registers are one single cycle. It's not exactly one cycle. Register reads actually take a few cycles in GPUs, and we'll see why when we look at the microarchitecture. But it's pipeline, so you can normally get one read per cycle out of these things. It's very fast. If you want to go to the per block shared memory, it's a few more cycles. So this is a bigger structure, so it takes a little bit longer to access it, but there's no tag lookups. There's none of that expensive caching stuff. So it's about 5 cycles. So it's almost as fast as your registers. And then there's this read-write per grid global memory. This is the sort of normal, quote unquote, normal memory. When you pass a pointer into your kernel, that's what you're pointing to. And this could be 500 cycles. Okay. If it's cached, if you have a GPU that has a cache on it, which most modern ones do, and you're lucky enough to hit within the cache, then the L1s can be 10 to 70 cycles. L2s can be 100, more than 100 cycles. The L1 hits on GPUs are typically very long, right? Even though you're hitting in the L1 on a CPU, your L1 hits usually like a cycle or two, right? That's the sort of 437 model. On a GPU, sometimes your L1 hits are like 70 cycles, which seems stupid, right? Because I'm not saving any latency, but it's still better. Why would it be better? Say, have a 70 cycle latency than maybe an 80 cycle latency at the L2. What are you saving if you hit in a high latency cache, even if the latency is no better than going to the L2 for some weird reason? Any intuition on this? Yep.
You don't have to go through. You don't have to go through PCIe to get to the RAM.
You don't have to go through PCIe. So we're not going through PCIe to get to the RAM. We're going through an on-chip interconnect. So that memory bandwidth, when anyone's bought a GPU and it says there's this many CUDA cores and this many terabytes of memory bandwidth, every time you miss in that cache, you're going out to that memory and you're sucking up bits of that memory bandwidth. Okay, so even though there's not a clear latency win in GPU caches, still a little bit of a latency win. And this will be true of everything we study in these throughput processors. There's a clear bandwidth win. The whole game here is trying to make sure you're efficiently using all of the bandwidth that's on this machine. If you're consistently missing in the cache, then all of those accesses have to go out over the pins. And now you're wasting that bandwidth that maybe you could have used on other threads that actually needed data that wasn't redundant. And you could keep the machine busier for longer. So even though there's not this sort of, and again, this is counterintuitive if you've spent your whole life just thinking about latency, which is really what CPUs do. But there's still a huge win here because GPUs, you'll see this sort of comment in papers that I'll get you to read. The caches act as a bandwidth filter. They're not really helping latency, but they're filtering the bandwidth. They're trying to make sure that you're not wasting bandwidth on redundant accesses and you're exploiting the locality. Okay. So that's the global memory. It's cached in most machines. And if you are unlucky enough to miss in the cache, you go all the way out to HBM and you have to trigger a page fault, or not even a page fault, a page table walk, you could be looking at 500 cycles. If you trigger a page fault, it's even longer because you now have to transfer the thing across the PCIe. Okay. Constant memory, there's a little cache on here. It's fairly efficient. It's about 5 cycles with the cache. And if not, you pay the sort of normal latency of going to the global memory. But typically you don't use a lot of constants. So constant cache uses a super high hit rate. Yes.
So if you're doing a reduction where let's say you have to access memory across threads, you use shared memory?
Yeah.
If you use shared memory, would you be limited to reducing what can fit in a block?
Yeah. So you'll have to make the program hierarchical. So you'd have to split your reduction up. The efficient way to do it is reduce first across the block and then reduce among blocks. Okay. So if you have a million threads, right, you don't want them all trying to reduce sort of together, right? Let's split it up. It forces you to naturally subdivide your program. And so I'll reduce first where it's fast, and then I'll only have one sort of global reduction I need to do per block. Make sense?
Yeah.
Other questions? And you can even bring this down to a warp. As we'll see, there's these things called warp synchronous instructions. So, instead of going to shared memory, maybe I'll just there are special instructions where if you want to reduce across all of the lanes in a warp, there's a magic instruction that will do that for you, right? And it will just, read from its own register file. And then when you reduce across the shared memory, it's only 1 value instead of 32 values. So an additional optimization on top of that. But most things here are focused on, forcing you to construct a good hierarchy in your program and exploiting locality where it exists. So, yeah, good question. Other questions? Yes.
If you constant memory have to be global memory because you guarantee not to do write backs?
That's correct. There's no write backs. There's no writes at all, right? So you can simplify this and
Just like half the eviction, basically.
it's just it's LRU based evictions. Well, loosely LRU. I don't know precisely what it is. Probably NRU or some simplistic replacement policy. But it makes things simpler because you don't even have a write path in the cache. You don't have to write back. You don't have to write through. You don't ever have to write, right? It's just sort of caching these constants. Okay. Other questions? Yeah.
Why do I think the error one latency is much longer than this?
Good question. So it doesn't have to be, but historically, the L1s in GPUs have been tacked onto texture L1s. They're texture caches. And we'll talk about texture caches later in the class when we start looking at a little bit of the graphics hardware that's programmable through CUDA. And texture caches are by their nature high latency because they don't care as much about the latency because they know that they've got, enough work to cover the latency. So they're just not built for it. So they have relatively deep pipelines within the cache. So even if you're processing the hit pipe, it simplifies the design of the cache to make the cache super latent. And if you don't care about being back in 1 cycle and you can tolerate 70 cycles, then you should design the cache that way. And that's the way texture caches were built. And so the early GPUs, like the earliest CUDA GPUs had no cache. Okay, it was just there was no L1s. And if you wanted to cache it, you had to explicitly put it through the texture cache. And there's these special weird operations in CUDA to go access the texture cache. And then they were like, well, maybe we want caching in some cases. So they started to add an L1 cache. And then the size of that thing was super small. So it was effectively useless. And then they started to make it bigger. And now today what happens is this shared memory space and the L1 space in your cores is dynamically adjusted based on your program. So since the programmer is deciding how much shared memory a kernel or each block in a kernel wants to use, if I write a kernel that has no shared memory, like that stupid one we wrote there, the one we wrote for the 2D blur, it doesn't use any shared memory. So the modern machines will look at that and say, okay, I'm going to use all that SRAM that was my scratch pad. I'm going to take it all and devote it to the L1 cache. And then if I actually explicitly use a bunch of the shared memory, I'm going to use as much of it as I need. Whatever is left over is going to go to the L1 cache. So the structure inside, the cache structure inside these cores today is adaptable. So it can sort of share itself between this shared memory and the L1 cache. Okay. Other questions? And we'll study this when we look at the microarchitecture. But the point of this slide so far is just to give you a sense of like, if we were only going to ever teach people CUDA and they didn't care about any of this hardware stuff, like this is what they would see for a programming model at its very basic level. Okay, shared memory, registers, global memory, and constant memory. Okay. Other questions here? All right. And the way we differentiate these is actually, the registers are obviously their own names, right? Like they have R1, R0, whatever. Each of the other memories is a chunk of the virtual address space will be devoted to each of these memories. And then we'll deal with pointing you at the right place in the translation logic. Okay, yeah, both global and that can have a cache IRB. So here's some examples of some chips. I didn't put a hopper in here, but essentially there's a theme, right? They just sort of keep getting bigger. This is a relatively recent one, circa 2018. This is a Volta. Maybe I did put it there. Anyway, I don't know. This is a Volta machine. So this sort of shows you, what is a 10,000-foot view of what the architecture looks like. This is what's in the sort of programming paper to give programmers a sense of, what the machine is, composed of at a very high level. Let me just highlight a few things on here before I move on. Give me 1 second. Okay, so the cores, right? When we were talking about SMs, that's what these are. So like all of these sort of sectors of 4 green, that's one SM, that's one core. And each of those cores can hold 32 or 64 threads. So they can hold 2048 threads. So each of these little groups of 4 green things can hold 2,000 threads. And then there's, I think, 80 or like 120, I can't remember on the Volta. Then there's 80 or 120 of these. So the total number of threads that can be, scheduled on the machine is 2,000 multiplied by, 1,000 or 100 roughly. Okay. Yes.
So the picture previously then was that a picture of one multiplies through that?
Yeah. So what this is showing, well, this is not. So again, the program, sort of is meant to naturally map to the architecture, but this is a picture of a program. Okay, this is sort of from the programmer's viewpoint. Like when I launch a kernel, it's called a grid. Okay, it's a bunch of threads together. That grid is composed of blocks, and then this is just showing you there is a tie-in to the architecture because that's why we start with the programming model, because it sort of shows you how you programmers are forced to use these things. It's showing you where each of those levels of memory conceptually is. Okay, and that does loosely tie to the machine. But if I'm trying to tie that previous picture with like this picture has no concept really of an SM, right? The programmer doesn't actually need to know how many SMs there are. The programmer just needs to know that I've got blocks in a grid and I have access to these memories. Okay. When they start trying to, optimize things, then you're going to have to worry about, well, how much shared memory does each individual SM have? And then how much shared memory is each of my blocks using? And you can imagine that there'll be these weird, what we call performance cliffs, where it's like, oh, if I just add one more thread to the thing, I can't fit a whole nother block on there. So now I have less work on the machine and everything collapses. So there's this sort of, and we'll deal with this when we talk about occupancy, hopefully today. There's this kind of like balance and like, well, how much of the machine am I using in the program? But from a 10,000-foot view, to just get something functional, the programmer really just needs to worry about blocks and grid. Okay, good question. Other question? Yeah.
This might be a complete misunderstanding. So you said that the shared memory and the L1 are kind of like dynamically allocated based on how much of this needed.
Right.
I'm assuming the shared memory is scratchpad memory.
Yeah.
So scratchpad isn't tagged, caches are tagged.
Right.
How exactly does it look architecture?
So basically you have unused tags when you're using the it is a scratch pad memory. You need CAMs, content addressable memory for the tags. If the whole thing is used for shared memory, you don't need the CAMs, so they sit there. It's very difficult to create a machine in which there's no waste, right? Like something is got to be in there that's not used all the time. And so, they've decided that tag overhead is worth the trade-off if the programmer is actually using the shared memory. Good question. Other questions? All right. So this is sort of each SM, and then there's a bazillion of these things, or I think 100 or 80, I can't remember. And then they get grouped into these things called TPCs. So then they have like another level. And again, we don't really need to worry about the TPCs too much. Actually, in Volta, a TPC, I think, is 2. And then each of the TPCs get grouped into these GPCs. And these names, TPC and GPC, are like graphics leftover. I think they're like I can't remember what they stand for. But they sort of group them together in a hierarchy. And the way they're connected to the interconnect is related to this hierarchy, okay? But not only from the programmer's perspective, all of these SMs are sort of peers in the system. And then they all go through the L2 cache, and that L2 cache is memory side. That's what this big chunk of stuff in the middle is. And then if they don't hit in the L2 cache, and that L2 cache is actually sprayed across each of these memory controllers logically, then they'll go to a memory controller and then out to whatever memory substrate they're using in the case of Volta HBM2. Okay, and you'll see that there's multiple memory controllers here, right? Which means that there are multiple independent channels to the memory system, which is not typical usually of a CPU unless it's a high bandwidth one, where you can literally have like each of these memory controllers represent discrete pins out to discrete memory chips. And they have their own, they have their own little queues inside of them that are doing memory scheduling and all this kind of stuff. And, if all of this is sort of like foreign to you at this point, that's okay. We're going to talk about the design of these things later as we talk about the architecture. But this is sort of a high level 10,000 foot view of what the thing looks like. And then there's this thing called the gigathread engine. What do you think that does? This is in hardware. What do you think it does? Yep.
Yeah, maybe like a scheduler.
A scheduler, yep. What do you think the gigathread engine schedules based on where it is? Blocks. That is the thread block scheduler. But thread block scheduler is not as sexy as gigathread scheduler, right? So that's what it's called. That's the thing that's distributing the work down to each of the SMs, this gigathread scheduler. And then there's a bunch of stuff on here to do the PCIe craziness. And then there's also they have a high-speed hub over here for what they call NVLink. NVLink is NVIDIA's proprietary high-speed interconnect to connect other GPUs together. If you have a data center node that's got like 8 or 16 GPUs in it, you don't want to go back over PCIe every time to do some kind of communication among each other. You want them to have fast communication together. This is obviously important in things like machine learning with huge scaled models that are distributed across multiple GPUs. You want them to be able to access each other's memory very fast. And so that's what the NVLink technology allows. Yes?
Using NVLink, do you connect the GPUs in a daisy chain manner or?
No, it's not daisy chain. You can do it however you like. NVLink is a point-to-point connection. In typical, 8 GPU machines, it looks something like this. I think it's like this. So there's like 4 that are completely connected, and then there's a bridge between the 2 groups of 4 to go across. I can't remember if there's more. Yeah, I think there's just 2 lines. So basically, you have much more speed here, right, or much more bandwidth here among these GPUs than you do to like go to the other GPU on the other side. Okay. Like DGX boxes, has anyone heard of these? These are like the sort of NVIDIA systems that they sell. This is typically how they're connected. Anyway, that's interesting, but not super important at this point. Other questions? Yeah.
How much of this is specific to NVIDIA GPUs versus like more general?
So the link technology is proprietary. Other vendors have different high-speed link technologies that have different names. Now, there's patents on NVLink. Like AMD cannot produce an NVLink connection. for example. I don't know what AMD calls theirs, but there's a name, like it's essentially like a communication protocol, right? Across, I mean, it's like SPI, right? From 362, like there's these protocols that exist. This one is particularly high speed, so you have to build the transceivers to basically handle this, and the communication protocol can be tailored for just, this one purpose, high bandwidth GPU traffic. So we won't get into the construction of these protocols. It's interesting, we could, but it's kind of very, very nitty-gritty detail. But every vendor that has inter-GPU connections has some kind of protocol that they're using for high bandwidth.
Also was asking about like just the general organization, like grouping
into these. So normally, yes. So most machines that have a lot of, so why do they group, right? They group because to connect all of these things to all these memory controllers, that's a lot of taps, right? Like if I think I'm going to connect, so I think maybe you're thinking about a daisy chain of like connecting the SMs, or at least the groups of SMs together as they sort of go around. Now GPUs, their traffic pattern is very unique versus a CPU. In a CPU, you want kind of exotic patterns because you will have CPU to CPU direct communication, right? Through what? What will do explicit CPU to CPU communication? What mechanism enables that? Coherence, right? If I've got a fully coherent system, I will share values between CPUs. I don't want to always have to go back out to the main memory system and then back down. GPUs don't have that, right? So that means my traffic pattern is explicitly all this way or all that way, right? So it's basically just like the cores puking stuff out to the memory and the memory taking stuff or giving stuff back down to them. There's no communication between each of them. So can anyone think of a good network for this? You guys studied networks in 666 yet? No? Maybe some VLSI people in here who sort of understand network design in some way. What would be a good network for such a traffic model where it's either all this way or all that way? You had a hand? Any guesses? Has anyone heard of a crossbar? Full all-to-all connection? We'll study this a little bit when we talk about the interconnect technology. But basically, you're going to have, all of the SMs potentially able to talk to all of the memory controllers. That's really the connection here. And then all the memory controllers potentially able to talk to all of the SMs. But the SMs can't talk to each other, and the memory controllers don't talk to each other. So it's a direct sort of communication between only SMs and memory controllers. And the way that you do this at high bandwidth is with a very simple, relatively simple interconnect, which is just a crossbar, which is good for this kind of traffic pattern, simple to build, not super area efficient, but you really do want to spend the area, because if you don't give this interconnect enough bandwidth, then you're going to starve the high bandwidth memories. So you have to make sure that there's enough bandwidth in that on-chip interconnect to feed the high bandwidth memory controllers. Okay, good question. Other questions? And again, if that term is foreign to you, that's fine. We'll look at it later. So there's a few other examples here of architectures. So this is the Turing architecture. So this one's smaller. It was actually a little bit, it's the generation after Volta. So this is 2019 that's covered up. This one was made specifically for graphics, okay, which is why it's smaller. So they don't sell a data center version of these Turing cards. And they added this little thing called the ray tracing core. Okay, so who's heard of ray tracing before? Okay, everybody. Where'd you hear ray tracing? Don't know what a crossbar is, but you know what ray tracing is? Aren't you hardware people? Where did you hear ray tracing? Just like on TV or something? Your phones do this? I don't know.
One NVIDIA, the NVIDIA promo for the RTX 20 series cards.
They talk about this.
Yeah.
Okay.
I actually have this card actually.
You have the same card. Okay.
Yeah.
It's like the first parallel program you build, right?
Ray tracing?
Yeah.
Is it? Where? Here? Who's teaching you guys ray tracing?
Textbooks.
Textbooks, okay. All right. I thought we just got you to do Ocean. Ray tracing is way cooler. Okay, ray tracing. Sounds like you all kind of know, right? So the rendering with triangles that I've been telling you about before, like this rasterization, this projection onto screens, it's a total hack, right? It's not how light actually works. So, for example, if you've got a raster-based screen and I want have a hockey player standing on ice, and I want that hockey player to have a reflection, so I can see like, I can see a reflection of him in that ice or on a mirror or whatever. What do you think you'd have to do in raster-based rendering? Any ideas on how you might achieve that? Manually what?
Like you'd have to actually replicate the thing.
You have to replicate it, right? So what, and this is what they do in video games, like there's a model of the dude standing on top of the ice, and then you take that same model and just flip it upside down, and then move it in the same way as the top one on top of the ice, and then just make the ice slightly transparent so you can see the second dude walking around upside down, right? So you fake it, right? You fake all of these effects that are in the real world because you're not actually describing the physics of how light works. Ray tracing is not like this. Ray tracing is shooting out these rays from the camera, and then those rays are bouncing off of stuff and picking up the colors of everything it bounces on. Okay, so and there's properties with the things that it bounces on. So when it bounces on the ice, that player's reflection will just sort of naturally show up if you throw enough rays at the scene, and the rays are sort of bouncing off him, bouncing off the ice, and then eventually bouncing back up to the camera, right? Which is what's happening with real light, right? It comes out, it picks up these colors, it sort of comes back into your eye, and then you sort of see the colors. And the more rays you cast, and the longer you let them sort of settle out, the more realistic the scene looks, okay? So ray tracing has been used for actually quite a long time in things like Disney Pixar movies, right? Like those scenes, you can just send it out to a render farm of a whole bunch of servers, right? And then wait 4 hours for each scene, and it'll be beautiful, and then wait 4 hours for the next frame, right? And then to do a whole movie, it takes you like 6 months or something on a bunch of computers, but it looks beautiful, and you have time because the movie's going to come out in 6 months anyway, right? Video games are not like that. We can't take 6 hours to do one frame. So real-time ray tracing is hard because fundamentally, the longer you let the rays bounce around, the better the scene looks. But you've got a 60th of a second. Okay, you've got 1/60th of a second, and you're going to show me the best thing that you've got. And it turns out that like historically, it's crap, right? Like ray tracing looks like crap in real time because you don't get enough of the reflections, and it looks way worse than the hacks we do with sort of this raster-based rendering. But it's gotten a lot better. The algorithms have gotten better, and then the hardware's just gotten faster and more parallel. And then they've actually made explicit cores for this now to try to make it that one extra bump better. So these things make it, their marketing is 8x faster than it would be without the cores, which is probably roughly true, at least on some scenes. But it sort of brings it closer to reality in sort of real time, okay, at a 60th or a 30th of a second. And I don't know what the current state of the art is here. There probably are games that are using or games or some kind of like three-dimensional rendering that are using ray tracing more regularly. You can also do a partial thing, right, where it's partially rasterized, partially ray traced. So like ray trace has these nice effects like this thing called ambient occlusion, right, where if you've got a big red wall and you're standing next to the red wall with white shirt on, like your shirt's going to look a little red, right? And ray tracing just sort of gives you that effect. And so sometimes they'll apply like specific ray tracing for specific effects, but not like the full on, like the world is blank and then I have to generate every color with the rays because that's more intensive. But anyway, so they've added these sort of ray tracing cores are specifically for graphics. Super interesting. Ray tracing is kind of this very cool thing that's kind of taking off in the graphics world. Yes.
A very big knob that the programmer can turn during ray tracing is how many times you want the ray to bounce before you stop the rendering.
Right.
Because it like just grows up exponentially if you have more than like 4 or 5 bounces.
Right. Yep. And then rays can like, they may scatter, right? It might not just be one ray that's created. It may hit something and then sort of refract, go in different direction. So like to really get something that's photorealistic, it's still very expensive. Graphics is always like this. It's a consistent trade-off between like how much time and resources you're willing to spend on the render and how good the render is going to look generally. Anyway, so that's what these little yellow things are. They added these ray tracing cores. They don't put these inside the server class chips because they're not meant for ray tracing, right? They're meant for running machine learning. And this is essentially unused if you're running machine learning at this point. Yeah.
Has anyone ever actually revealed how the RT cores actually work? Or?
Not really. So, I mean, there's very like cursory information on what they're doing. They're basically making these intersection tests very fast. So ray tracing is a bunch of just intersections, right? It's like did the ray hit this thing? It's a bunch of math to figure out, hey, did I hit this particular object? These things, instead of taking like 100 or 150 instructions to figure out if things intersect, they can do it in one instruction. So that's the basics of what they're doing. The guts of it is completely proprietary. AMD also has ray tracing cores, and their ISA is open source, so you can look at the instructions associated with each of the RT cores. You can glean some information from there. I had a student do an internship at AMD, so he knows exactly what they're doing, but he can't tell me technically. And he's never told me. Yeah, question.
Aren't you writing a paper on an open source ray tracing?
Yeah, no, we have a paper that's okay. So we have a paper that's trying to take these things and try to, make them more amenable to general purpose programs. So ray tracing, you can sort of look at it like CUDA, right? Like right now there are people who have hacked ray tracing cores to make them work really well on graph processing applications. But like trying to write a graph processing application as a graphics rendering with a ray tracing software is a huge pain in the butt. So we've got some work on trying to like make that look more like CUDA, right? So like, how could you generalize these things so they work well for the graphics, but also target these other sort of, because it's a super irregular workload, right? It's not like the traditional everything lines up workload in a GPU. There's like stuff bouncing off stuff all over the place. Memory accesses are a mess, right? So it would be nice to have something that accelerates that type of program. And yeah, we've got some work taking a look at that. Not published yet. So yeah. Other questions? All right. Ampere. So I did keep going. Okay, so Ampere. So they just keep getting bigger, right? So Ampere is sort of after Volta. So the general thing is here is you have more transistors, so you add more SMs, you add more memory controllers. This one actually has two sort of distinct planes. We think that this is essentially a chiplet-based design. I don't know that that's explicitly mentioned, but you can see how there's a partition here between the two sort of large pieces of the chip that are connected via the L2 cache. And again, it looks like the Volta, except there's just way more everything. And the architecture changes a little bit, and we'll talk about tensor cores as we get deeper into the class, but they just sort of keep getting bigger. And this is Hopper, so I did put this in here. So again, it went bigger, one step bigger, right? So now you've got 144 SMs, you have more memory controllers. This embarrassingly parallel workloads and embarrassingly parallel hardware like GPUs, sort of eats up Moore's law as long as it's gonna last, right? Well, we'll eat up as many transistors as can be given economically to sort of fill out these things with more compute, more bandwidth, et cetera. And as long as your programs scale, everyone's happy and everything gets faster. Or you can run bigger programs or whatever. So H100, this is the most recent iteration of the NVIDIA GPUs. And again, I'm focusing on NVIDIA because we're doing CUDA, but there are equivalents for AMD, right? Every one of these has a competitor roughly in AMD hardware. Designed slightly different, but they're all violating each other's patents, right? Like basically, I was talking to engineers at both companies, and it's like, you cannot build a GPU today without violating like 100 patents from NVIDIA and 100 patents from AMD. And they each just co-violate, and it's like mutually assured destruction, right? Like, you can't come after me because I'm going to come after you. So the world just kind of works, right? So, so they all sort of look the same, right? But they're named differently, and, they're different companies, et cetera. But the basic principles of this, there are some different subtly microarchitectural, and we'll touch on that. But the general philosophy is the same. Yes.
If you put a GPU, the same SoC as all the memories and stuff,
yeah,
does that give you more flexibility in how the GPU can look like?
It usually doesn't, right? Because if you're putting it on the same die as this other stuff, like this die is monolithic. Well, I mean, it's probably two chiplets, but each chiplet itself is like homogeneous. It's just got SMs on it. If you start adding all of this other stuff, I don't know. I mean, I don't know what you mean by flexibility. Like, yes, there'll be other things on there, but it's probably less efficient than if you just rolled it like this. If you are only concerned with GPU throughput. I mean, this is the reason why they're still discrete. because it's just better to have them live alone with their own super high bandwidth memory system than to try to bolt them together with the CPU. And that's a bigger win than the overhead of communication to go back and forth. Make sense? Other questions? All right. So this is just a little bit more on thread blocks and SMs. We touched on this a little bit before, more explicitly here. Every SM can take multiple of these thread blocks, and they do it this way to try to maximize resource usage. Typically, the total number of threads that can be in a thread block is 1K to 2K, just depending on the architecture. The typical number of threads that can be on an SM is typically, again, 1K to 2K, depending on the architecture. I don't think blocks can ever be 2K. I think the biggest blocks are only ever 1K. And again, you can ask why these numbers. They are what they are, right? It's just sort of the trade-off that they have selected for the size of each of their individual cores based on, economically viable ways that they can produce these things. When I put multiple thread blocks on each SM, the threads will run concurrently. Okay, so that means that each of the blocks could be scheduled, at the same time as other blocks that are on the same core. They will sort of time slice themselves over the resources available to that core through a scheduling mechanism. And the SM, so inside of the SM, there is hardware that manages this real-time scheduling, this cycle-by-cycle scheduling of which warp is going to get the issue and instruction next. Sort of like how on a CPU, you've got, you basically got your instruction queue, right, for your single thread, and you've got all the independent work, and then you've got a scheduler trying to decide which instruction to pick out that's independent that go into the pipeline. We have a similar scheduler here, except that we have guaranteed independence among all of the warps, right? So you've got 64 warps on the machine. I know that if I take an instruction from warp 0 and then take an instruction from warp 7, they're not going to collide because they're guaranteed to be independent. Sort of like it's explicitly giving you a whole bunch of independent work. The side effect of this is that you can't really say what SM your block is going to go on easily anyway. And you can't say or know specifically what the scheduling algorithm is going to be. And the machine is sort of trying to figure out what the best scheduling algorithm is on the fly. It's a heuristic, and those things are proprietary. And again, as a programmer, you really don't need to know. If you wanted them to go in any particular schedule, you need to use some kind of synchronization like barriers, et cetera, to ensure that they're stopping before you sort of move on. Other questions here? All right, what's inside each SM? So I pulled out basically that big picture, right? This is a zoom in to one of these SMs. This is a Volta SM, so from a few years ago, although the hopper looks surprisingly similar, or maybe unsurprisingly similar. So an SM has an L1 cache, an L1 instruction cache, and then, in recent generations, they've started dividing them into these things called subcores, okay, which are effectively like their own little cores. And each of these subcores has its own sort of L0 cache. It has its own scheduler to figure out which warps are going to be scheduled to resources on that core. And it's got, 1/4 of the register file that's on the SM. So, in this particular architecture, you've got 16,000 32-bit registers, okay, in each of these subcores. And then each of these little boxes, again, this is kind of a marketing picture, right? But each of these little boxes is effectively one lane of a particular operation, okay? So what this says is I've got, I think, 16 int32 boxes here in each core. So that means that to clear one warp instruction, if it's doing it regular int32 operations, it's going to take 2 cycles, okay? Because a warp is 32 threads. This is effectively the SIMD width of the real machine. So this is highlighting the fact that even if your warp is a certain size, your SIMD can be smaller, and you just issue it over what we call multiple beats, right? So in this case, with the Volta, since you only have 16 lanes, it's 2 beats to issue each warp. We have a different pipeline for integer versus floating point, so there's sort of parallel pipelines. We have a different pipeline for floating point 16, which has half the throughput of the other pipelines. That's why there's only 8 of those instead of 16. And then we have, effectively a bunch of what, load store units which have a throughput of, they basically can do 8 threads per cycle. So it takes 4 cycles to clear them, nominally in a 32 wide port. And then we have even less SFUs, right? I think there's only 4 of these. So SFU stands for special function unit. This is things like tangents, like, division or reciprocal operations, stuff that, is computationally intensive, that your program better not have a lot of, or else it's going to be slow. And the bandwidth of those is only 4 lanes per cycle effectively. And then you've got this big blob called tensor core, which is essentially the matrix multiplication unit that lives inside the GPU. Okay. So who's heard of TPU? Everybody probably 565, I think at least touches on it. Tensor processing unit. This is the thing from Google. You can't buy one. I think you rent time on them now, right? You can pay them and log into servers. But the TPU is basically a big data flow matrix engine, which makes it more efficient to do matrix multiplication, which at its core is what most of the sort of machine learning that's driving the world is. It's matrix multiplication. So in response to that, and this sort of NVIDIA also observed the same thing. They didn't build their own TPU, which is just a big gem unit. They basically built little TPUs, little gem units that they stuck inside of each core. And this is what's called the tensor core. And these have a lot higher throughput. They're a lot more efficient when you're doing dense matrix operations. Okay. And we'll talk about how this works and why it's better when we get to the hardware design. But any optimized kernel in modern GPUs that's running dense gems is using these tensor cores. They have access to wide sort of matrix registers. The computation takes place on sort of matrix-based data. There's data flow inside these things to make them more efficient. So, there's sort of much more, it's much higher throughput to run dense matrix through the tensor core than it is to do it through the normal floating point 32 units. Yeah.
Did you make Google so like little TPUs there?
Like consumer-based TPUs you can buy?
Yeah.
Okay. For like embedded systems?
Yeah.
Okay. Interesting. Yep. It's good to know.
If CUDA did allow you to map bread blocks onto specific SIMs.
Yep.
Would there be any benefit from the programmer's perspective? Like, could you use it in a way that we use shared memory inside of the bread block?
I mean, if you're doing something relatively simple, probably no. Right? The runtime schedule is probably better than any schedule you can dream up. If you're doing something kind of weird that the runtime scheduler for the blocks is not anticipating and handling well, then possibly. And you can do that. You can basically do that by writing inside your CUDA program. You can read what SM you're on. So at the very beginning of your CUDA kernel, you can say, if SM0 do this, if SM1 do this, and then effectively have them do different things. Right? But it's kind of a mess, right? You're sort of taking on all of that in the program itself, which makes the program ugly. But that's how you could do something like that. But typically, it's usually not better. Like, unless you've got something very specific that you want to do, that the default scheduler is not doing well for you, then you probably just want the default thing to handle it.
Is there a reason why they don't even allow you to do that?
Part of it is it makes the program now extremely architecture specific. So one of the beauties of these things is that I can take 100 programs that all worked on Volta, and then I can just throw them at a Hopper and it all just works. Or vice versa. I write it for Hopper and then I throw it at a Volta and it works. If I wrote it for Hopper, I'm trying to use SM144 and then I run it on a Volta, it's gonna be like, there is no SM144 and now it doesn't work, right? So it breaks that sort of, interoperability of the programs. Again, if programmers really want to be super clever, you can go ahead and do that, but it probably matters in less cases than you intuitively think. Like, you're probably better off just letting it handle it unless there's a compelling reason not to. Okay. Yeah.
If you have an SoC that has a CPU, a
Yeah.
GPU with tensor core, a TPU, and an NPU, how do you decide what part of the workload works there?
Yeah, that's a good question. I mean, this is a topic of like 100, like system software type papers. Like, I have an SoC, I've got a program that's got this kind of demand. I've got these, this is the problem of the next 10 years, right? Is I've got a plethora of different accelerators I got a program, I got like 100 different programs with varying demand. How do I map those things to the right accelerator? That's a challenge. And the optimal solution, like it's all some sort of heuristic based thing, right? And then, well, I don't know, maybe it's so big that I want to use I have a giant matrix where I want to use the TPU and I want to use the MPU and I want to use the tensor cores. So I spray the whole thing across all of them. Now I have to deal with orchestrating, putting the thing back together again. So then was it worth it? Or should I just have only done it on the TPU? And again, is this an SoC that's like driving a rendering display on an Oculus? Like then I need to use the GPU for those graphics. So am I going to waste graphics on this other stuff that the TPU can do? So these are, I mean, look, some of you will get hired to be like engineers at Qualcomm or something. And like, that's what you're going to do all day is like figure out, I have this workload, there's these speeds and feeds on all these different things on this SoC. How do I schedule it properly? And how do I build the system so that the speeds and feeds all make sense? Like there's no one answer. It really just depends on what your workload is. It's like security, right? It's like you'll never actually fix the problem. There'll always be something to work on in that space. Other questions? Yeah.
So all of these functional units that are in this diagram, like are those all like single cycle or are they pipelined?
They're pipelined.
Yeah. In that case, like do you have situations where a single kernel might use like multiple of them, like if you're your user the FP32 and you're also using the tensor core for me.
Yeah. So you would like if I had a kernel, like let's take a simple case, we just have one warp on one of these subcores. So there's 4 schedulers, right? So each scheduler gets a subset of the warps that are assigned to this SM and says, I'm going to manage this subset. Okay. So let's say the warp 0 gets scheduled, like assigned to the upper left subcore. If that program has an int32 operation, a floating point 32 operation, a floating point 64 operation, a load, and like a reciprocal, one after the other, all independent of each other, which is weird, but maybe happens, right? In one cycle, I can issue to the FP32, and the next cycle, I can issue to the FP64 or whatever. Like you can like build this thing up. And then you've got awaiting result dependencies, et cetera. And there's no forwarding, right? So it's basically implemented through stalling, some basic scoreboarding. And again, we will talk about the nitty gritty details of how this works when we get to the microcontroller part. But yes, you can. Yep.
Is there any dark silicon on the GPU?
What do you mean by that?
Prevents you from lighting up all the cores at the all the functional units at the same time?
No, but there is DVFS. Okay, so dynamic voltage frequency scaling. So you're not pegged at a particular frequency. If you don't need to have the voltage and frequency be high, it'll dial it back. If you start lighting up all the cores, it'll ramp it up. If you're hitting power limits, it'll ramp DVFS down to make sure your thing doesn't overheat, right? So that is a knob it has to play with. Does it explicitly darken silicon? No. Dark silicon, there's a paper on this, right? Like, it's sort of like this term, but companies don't habitually produce chips that are going to have dark silicon on them, right? They usually are able to scale things back. Like there's different levels of dark silicon, right? You could say that if you're not using the tensor cores, those tensor cores are dark, right? In that program we just wrote, if you ran it on this machine, like not going to use that pipeline. Is that dark silicon? I mean, it's unused silicon. So, if you look at it that way, then yes, there's like some waste there. But will it like explicitly turn off whole SMs because of some, it'll power gate them, certainly, right? If you're not actually assigned any work to them, it'll clock gate them, it'll power gate them. Like if it's off long enough, right, it'll power gate because that it takes time to turn the power back on. So again, it's trying to play these dynamic runtime games. So in that way, yes, it can turn stuff off if it's not using it. When I think dark silicon, I sort of think like, and maybe this is the wrong way to think about it. Like, I'm just going to take this whole thing, part of the chip, and just explicitly turn it off. And I know it's off like the whole time to power this piece. It's more dynamic than that, I think. And it's based on the demand. Yeah. Other questions? Yeah.
So what in the case if I want to use like int8, int4, are those all subsets of int32 or?
So in some cases, yes. So it depends on the machine. The tensor cores in particular, like this is Volta, so they only dealt with FP16 data. the newer ones, you can deal with lower precision stuff. I think there are lower precision explicit pipelines. If you can still operate on 4-bit data, but you're just gonna, if it's on Volta and there is no explicit int4 pipeline, then it's gonna go through the int32 basically. Okay. Yeah.
In that case, can't you pack all those in?
You could, but you probably won't. Right? So you think about the implications on the software there. You have one warp that, I mean, it's possible, right? If I have an int4 operation, I know now I only need a fourth of the bandwidth I needed before, and so maybe I could do it in one beat. But then like now some of my instructions are 4 beats and some of my instructions that are ints are going to be, so you could do it, but like it adds the complexity of the machine and what's the win, right?
Would you just take the L on like overflows? Don't be fun.
Other questions? All right. Let's see. Okay, so blah blah blah. So yeah, these things are statically partitioned. So you'll notice that like the shared memory. Oh yeah, I didn't talk about the shared parts. So that's each of the subcores. The memory system is shared among the subcores on the core. Okay, so this is an SM, right? From the programmer's perspective, this is what an SM looks like. It's got this internal subdivision, but the programmer doesn't really deal with this internal subdivision that much. And the memory system is shared between all of these 4 subcores. Okay, so basically the L1 cache, the shared memory, the texture memory, if you're dealing with rendering stuff, all of that is sort of shared and cut up statically among all the warps that you schedule. Okay, so when I put a block on here, the block says, okay, I've got 4 warps. I need a meg of shared memory. So it'll take the meg, it'll schedule the 4 warps, each of these cores, it'll take 1/4, or it'll take basically as many registers as those warps need from each of these places, and then it'll start running, okay? And so this gets cut up sort of, we're saying statically because it's when the kernel is launched. It's not really static, it's more dynamic, right? The word static probably is the wrong way to describe it, but it's not flexible. Like as this sort of program, as a warp is running, it's not giving up registers and giving it to other warps. It's like the warp starts and carves out a big chunk of the register file space, and then it keeps that until the warp is done.
So is the L1 data cache, is that like the scratch pad thing?
So the L1 data cache so the SRAM structure itself is shared with the shared memory. So the more shared memory you use, the less L1 data cache you have in this architecture, okay? And in pretty much all architectures now, most of them do this. But the data cache is the cache to the global memory, to the read-write global memory. So whenever you malloc something and then you access that array, right, that's going to be cached in this L1 data cache, okay? Yeah.
So in this is the subcore architecture.
Correct.
So in this case, can I do something like, hey, core 1 is going to write something to the shared memory, and then core 3 can read that shared memory?
Yeah. So again, as a programmer, you don't even realize that this subcore is here. This is just an SM. Okay. I probably should have started with an older model, but they all look like this now. So I decided to start with the Volta. To a programmer, your block goes on here, right? Your block gets some chunk of this light blue thing, and the guts of this is going to decide how to spray your block across the 4 subcores, and you don't need to worry about how that works. You just know that it's going to get on there, and they can read and write from the shared memory. If you're designing the hardware, obviously you have to worry about that, but like as a programmer, you don't really worry about it that much. Okay. There are these bizarre implications of this subcore thing. We did a paper on it, but again, it's sort of like, if you're just learning how to do CUDA, you don't really need to worry about the subcore thing too much. You just sort of know that this is what an SM looks like. Other questions? Okay. So there's a finite number of threads, a finite number of warps, and a finite number of thread blocks that can be managed at once in this SM. And so every architecture is different. There'll be some spec that's basically in the specs of the architecture. And then programs that you launch on this will take up as much as they need to run. And then as soon as they run out, they'll be like, well, I can't do any more work. And the other stuff will get queued. This is what's inside the Turing SM. So a little bit less complicated. So it doesn't have this, or it does still have the subcoring, but there's obviously less compute resources. There's what are they missing? Yeah, there's basically less load store resources. There's the same amount of SFU. They actually had more tensor cores because this is a newer architecture. Cache is a little bit smaller, and then they bolted on this RT core thing to try to make ray tracing go fast. Right, this is the Volta SM this is the one we just looked at. Okay. Questions on this? We will cover this architecture in a lot more detail, but I just wanted to give you a sense of, because we're going to start talking about occupancy and these kinds of things. So I want to give you a sense of what the SMs look like. Yeah.
It said that the L1 and shared memory share the same space. So
Yep.
I mean, like if the programmer explicitly uses all the shared memory space, then there'll be like no L1 caches.
So there's always at least a little bit. Okay. So I think it reserves like 16K or something. So if you use a very small amount will always be devoted to the L1 cache, but you could completely just bypass the whole system. And yeah, you just have no L1 hits. You just go to L2 every time. Yep.
Are there any accelerators that just do ray tracing and nothing else?
That's a good question. Probably. Are there any successful ones? Not that I know of.
I guess, for example, for something like tensor cores, right? They appeared in the GPU and then kind of become their own accelerator.
Well, I mean, I think Google did it first. I mean, it was sort of close, but yeah. I mean, look, I am 100% confident that researchers have proposed and maybe even taped out RT specific chips. Have they been sold and used? Not at the level of, like, GPUs are already like embedded in the graphics market, right? Like you're already buying them to render stuff. Now they're also good at this other complex rendering technique. So yeah, I don't know that there's like a big, academically probably, but like, is there a market for an explicit ray tracing accelerator? I guess not yet, right? Remember that line, that bar, right, of NVIDIA's stock price, where it was sort of flat, like that is like, markets have just only so much they can provide, right? There's only so much money people are going to spend on things, and rendering is much, much smaller capacity than machine learning. It's going to, run everything. So, you'd have to have a huge advantage and a huge market to try to spin up a whole other company that's going to come in and try to supplant GPUs and ray tracing acceleration. Maybe that exists. Maybe there's somebody trying to do it, but I don't know of it off the top of my head.
It's more like for like $4,000 AR headsets.
Okay.
You can add this extra ray tracing accelerator.
Yeah, but you've already got a GPU in there, and AMD or NVIDIA put a ray tracing unit in there, and they're probably giving it to you cheaper because they're selling way more of them, and now your boutique company needs to charge them some ridiculous amount for the small amount. Like, it's hard. It's hard to beat big companies, right, when they're competing in the same thing that you were doing. Question? Yeah.
Some have instruction data gets separately.
Sorry.
Some have instruction data gets separately or.
Do they do instructions separately or together? Do you mean? So each of those warp schedulers will essentially issue instructions from independent warps. So they will all be doing, if you launch a kernel, they'll all be running essentially the same code, right? Like the program counter, all the SMs will start off in the same place effectively. And then they'll start moving through the program, but they don't go in lockstep. They're all independent, like they're all independently scheduled. Is that your question?
So like in CPU we have instruction I-cache and D-cache.
Yeah. Yeah.
How does that work?
There's an I-cache and D-cache here. The I-cache the hit rate is insane. GPU programs are like are relatively small compared to like CPUs. You're like loading in Linux shared object files, and you've got like 4 megabyte binaries, and like, I-caches are important. In GPUs, like even inside, the research facilities at these companies, they just assume the I-cache hit rate is 100%, because it's like, the programs are usually so small and all the threads are traversing the same code that it's like, it's effectively 100% usually. Now, that's not true. If you get more complex programs, or maybe like some of these crazy, maybe machine learning executables that have huge code footprints, if they've like have highly optimized unrolled code or something, that might be important. But typically the I-cache hit rate is super, super high. There's a separate I and D cache. Was that your question? And it's backed up by main memory, right? So like the program lives in the HBM, and then it gets sort of dynamically read into the SM as it starts executing. There's a level of prefetching that happens there too, right? Like if you know you're gonna like give me the first meg of the thing and put it in the L1 iCache, right? It's an easy thing to prefetch. Other questions? Okay. We're gonna start on, we have like 2 minutes, so I'll just give you a preview on what we're gonna talk about next. We're gonna talk about occupancy. What is that? Oh, I know what that is. When I made these things, the online videos, my face must be down there. I think that's what happened. And then the guy who was making them complained and said, hey, your slides, like, I want to put your face there. So I think I put a block over there, so I didn't put any words there. That's what that is. I think, anyway, sorry about that. It looks weird. All right, so occupancy. So very quickly, what does this mean? It's really important when you're trying to figure out if your program is going to work well on the GPU you're using, okay? So that thread block scheduler, or that gigafred engine, it's assigning thread blocks to SMs, okay? Thread blocks will use less resources than the SM has. So every thread block has a bunch of factors that could potentially limit how many thread blocks you get on each SM, because each SM has finite resources, each thread block demands finite resources. So it's kind of like a packing problem, right? Of trying to like take all these thread blocks and pack them into all these cores. So the things that can limit how many thread blocks you get on a core are just the number of threads a core can handle. Okay, so there's only so much scheduling logic. There's only so many like scheduling slots you can pick between. So there's only so many warps you can put on each core. So you might just run out of threads, right? And that's kind of the ideal case if you're talking about maximizing parallelism. That means you're using all of the context that you can inside the GPU. So number of threads can limit how many thread blocks go on a core. Number of thread blocks can also limit how many can go on a core. So if your thread blocks are super small, like just one warp, you can't just put, 64 thread blocks on a core. And the reason for this is that there's certain resources associated with each thread block. This fast synchronization mechanism that they have, like there's certain hardware resources that are allocated to that, et cetera. So, each your blocks have to be big enough that you're not going to run out of those thread block resources either. Registers, this is a big one, and this one is a little bit trickier to manage because the compiler gets in the way here, right? You as a programmer have control over how many threads are in each thread block, how big they are, which can affect those first two numbers. The number of registers used in each thread block is dependent on how the code is compiled. If the compiler is doing aggressive optimization, it may unroll all your loops. And if you remember 565, if you unroll loops, you need more registers, right? Because you're effectively not reusing the registers every time you iterate over the loop. And the more registers that each individual thread needs, that means each individual warp needs more registers, which means that when I cut out my register file, I'll have less and less warps that I can run. So registers can also limit this, and this thing called in the shared memory, right? So you're going to explicitly say, I want a meg of shared memory for all these threads in the block, or whatever. A meg is too much. There's only 196K maximum on these. So maybe let's say you want 32K for each block. Then that means that if you have 64K worth of shared memory, that means you can only fit 2 blocks on there. And then you might not be using all the warp scheduling slots or all the register file. So you end up being limited by whichever one of these resources runs out first, okay? And there isn't like a perfect answer for which one you want to run first. And it's incredibly difficult to impossible to run out of all of them equally, right? That would be sort of the optimal, right? Like I pushed them all and used them all, I used up all the resources, but depending on how the program is, the nature of the code and the level of parallelism you have, it's practically impossible to run out of all of them at the same time. So when you spawn your kernel, all of these things will be known, okay? And then the GigaThread scheduler will take this into account, the thread block scheduler will take this into account as it sort of packs the work down into each core. And you'll find yourself, and we'll go through a couple of examples, trying to tune how big your blocks are to try to make sure you don't like screw up the occupancy. Right? Usually the first reason why your thing doesn't run well is you don't have enough threads on the GPU. It's probably because you've done something here that screws up the occupancy. So then the first order bit to try to optimize the GPU program is to play with that, so that way you can maximize the occupancy, try to get more work on there. Yeah.
Does that mean when you run across different GPUs, you'll have to find different?
Yeah, so this you do have to tune, unfortunately, right? You don't have to tune the program necessarily. It's usually just some constants on like how big your blocks are, or whatever. But, you know, as you move to different architectures, so this will be dependent on the architecture. So when I say Volta or Turing or whatever, that is the composition of the core. That doesn't change between product lines of the same architecture. So like Volta has a V100, which is like a high-end data center. You can buy a Volta that's an RTX that you can run graphics on. The same thread block configuration will make the most sense on both of because the core is the same. The difference is that the high-end one has like twice the cores as the little one, but the core architecture is the same. So you have to optimize this for each architecture. And libraries sort of do this for you, right? Like if you're using machine learning and you're using cuDNN or PyTorch and all the backends associated with cuDNN, like they do all this work on each release. When they release the new card, they'll be like, let's screw with it to try to like make it fit as best as possible on this new card that comes out. But you as CUDA programmers in this class, you have to screw with this manually because like that we're forcing you to do that. Okay. And so we're going to talk a little bit about that next lecture. Any questions on this? All right, that's it. We're done. We'll come back on Tuesday. Thank you guys.
Hey, Dr. Rogers.
Yeah.
Do you have like 15-20 minutes available anytime today?
Is it for the
Vortex.